Alright guys, so this quick video will help you with the last bit of material that we didn't get a chance to do today, but that will be asked about in page 205, questions 51 to 55, 61, 63 to 71, or 63 and 71 odd. So the first thing that I want to talk to you guys about is what are heats of formation. So heats of formation are symbolized as delta H sub F, and they're basically experimentally measured values that are taken during synthesis reactions. So for instance, here's a synthesis reaction where you take magnesium and oxygen, you make magnesium oxide. What essentially delta H sub F represents is the energy that's taken in or released in the process of forming magnesium oxide. So it's either the energy that's taken or released in the process of making bonds between the magnesium and the oxygen, or in terms of breaking bonds that might be present here in this reorganization. There's an appendix in the back of the book on page 1112 that lists the heats of formation for many common compounds. I'll show it to you. It's essentially tables that look like this. And so the heat of formation is in the first column. The heat of formation, note the units, it's in kilojoules per mole. So when you determine these things, essentially what you're doing is you're doing a calorimetry experiment. You're figuring what Q is for a reaction, and you're that value
from the heats of formation of benzene, oxygen, carbon dioxide, and water. Alright? So, the way that you do this is you go to the back of the book. Alright? And, again, the change in enthalpy is equal to the change in enthalpy for the reaction, so the heats of formation of the products minus the heats of formation of the reactants. Alright? And so if you look here, here are my products. So I've got carbon dioxide. These numbers that you come up with that you pull from the back of the book are in kilojoules per mole. If you look at the equation says that you should have 6 moles of carbon dioxide that you make. So, you're going to do 6 times the heat of formation of carbon dioxide from the table, and it has the carbon dioxide that you choose has to be the gaseous form. We're going to look up dioxide. Okay, CO2 gas plus 3 times the heat of formation for water. And it has to be liquid water. So we're going to look up water on this table too. So let's take a look here. Let's find H2O. Okay, it's over here actually in the oxygen section. So we look up the heat of formation for liquid water. You have to look at the state -253. Alright, so there we go. Right there within those brackets we have calculated the sum of the heats of formation of the product. So really the formula up here shouldn't just be delta H equals HF products minus HF reactants. It's the sum of the products minus the sum of the reactants. Okay? Alright, so now let's do it for the reactants. Alright, and again, if you realize here I multiplied the heat of formation for water by 3 because the coefficient here was 3. This was per mole, and I have 3 moles in the equation. Alright, if we do it for the products, you notice there's 1 mole of benzene. So it's going to be 1 times the delta HF for benzene. Okay, we'll look that up. It's liquid benzene, which has a value that's different from gaseous benzene. So again, be very careful by looking at the states and picking the right one. The delta HF for benzene in the liquid state is 49 kilojoules per mole. And then, according to the equation, we have 15 halves as a coefficient in front of oxygen, so we have 15 halves times whatever the HF for gaseous oxygen is. But if you look, the delta HF for gaseous oxygen is 0. But we knew that. We didn't really have to look that up. And that's because, again, delta H is the heat formation for stable forms is 0. Okay. All right. So and they want me to calculate it
from these elementary steps
that would normally be found in a mechanism. So the way that this forms, we think that it's the three-step process. These are the three steps. All right, well, first of all, we have to figure out how to manipulate these individual lines so that then when we add them together, we end up with that one, with the overall. So this is the overall equation. These are the elementary steps. Okay, so let's take a look here. If you notice, that compound right there, if you remember, that's called ethyne, is on the right-hand side in the overall equation, but it happens to be on the left-hand side in one of the elementary steps. So I'm going to have to flip this first equation before I add the three lines together. All right, so if I flip this equation, then my delta H changes to positive. Okay, so if you remember with equilibrium, it's actually the reciprocal here. No, it's just a change in sign. It's a little different. All right, so now I have ethyne in the proper place. Okay, so now the other thing that you should notice, so we got to figure out what to do with the next two steps, steps 2 and 3, is that the overall equation doesn't have carbon dioxide and water in them. So we're going to have to get rid of them. And so that means that we should have carbon dioxide on the right-hand side, water on that right-hand side, so that when you add the equations together, we cross them out because they appear on both sides of the arrow. So right now, as is, the way these equations are written, it appears to be okay. All right? The orientation is correct. So they're on the correct side, they're on the right-hand side where I need them to cancel out. The issue, though, is that the coefficients aren't quite right. Because in the overall equation, we should have twice as much carbon as is present in that second line. And, well, you would need twice as much carbon dioxide in the second line to get rid of the 2 CO2s that were in the first line. So we're going to have to take this second equation and double it. So we're going to have to multiply this by 2, right? So it becomes 2C plus 2O2 yields 2CO2. All right, well, how does that change the delta H for that preliminary step, that elementary step? It just doubles it. So you do 2 times negative 393.5 kilojoules. Okay, finally, the last step, I think it's going to be okay. We can leave it alone because water's on the right-hand side, and it's going to cancel out with the water on the left-hand side. And you have 1 and 1, so there shouldn't be any waters left over on either side. So I think that last step is good. So I'm just going to rewrite it down below. Okay, and so then delta H doesn't change. Okay, so now I'm going to add the three lines together, okay, and get rid of things that appear to be AKA spectators. So water's a spectator, carbon dioxide's a spectator. If we add up the oxygens, I end up with 5 halves. I'm sorry, do I? Hang on, let's see. Yeah, I end up with 5 halves. And I have 5 halves over there. That becomes a spectator too. And when I add up what's left, you end up with 2C plus H2 yields C2H2 fabulous, which is my overall equation. All right, that's my overall equation. All right, well, how do I get delta H now? I take all of these, and that's for this reaction, I take all of these individual delta H's for each individual step, ones that have been manipulated because we had to reverse an equation or change the coefficients, and then I just add them up. All right? So then the delta H of the reaction is going to be 1299.6 plus 2 times negative 393.5 minus 285.8, and I get positive 226.8 kilojoules. All right? Okay, so that's all you really need to do for the rest of the homework tonight. When I see you again on Monday, please have these questions done and have the Flynn reactions packet done. This essentially is all of, I believe, Chapter 5. When I see you on Monday, we're going to jump back to Chapter 18.
and we'll start talking about entropy and spontaneity and all that fun stuff, and we should be able to get all of Chapter 18 done on Monday as well. It's really easy stuff, okay? If you have any questions, save them for Monday.